Hi there, I'm Graham Lewis, and in this short video we're going to look at the chi-squared test of homogeneity and also look at the standardized residuals to see if there's a difference if we do reject H0. Now I would recommend, if you haven't watched my video on chi-squared goodness of fit, to watch that first, because that will go through the mechanics in more detail in this video. I'm assuming you know and understand how to do the chi-squared goodness of fit. So homo in Latin means the same. So what are we looking for in a chi-squared homogeneity test is whether two different distributions are the same, rather than in the goodness of fit test when we had one distribution and we wanted to see if it was fitted a set distribution. So one question that's always on students' mind is, imagine you're in a different class. Is a teacher a harder marker? So imagine we have two different teachers teach the same course, and students do exactly the same exam. Does this sound familiar? Is there a difference in the results of the two tests across classes? So let's imagine we've got Professor Alpha and Professor Beta, and we've got the number of grades given here. So for example, if I go here, we've got 3 A grades from Professor Alpha, 11 B grades for Professor Alpha, etc. So these green numbers are the observed grades of that professor. Professor Beta got 9 A grades, 12 B, 8 C, and so on. So we want to know if Professor Alpha or Beta is a harder marker, and is there any statistical evidence for this. So the first thing to do is to work out the expected counts if they were in fact equal at marking, which is what we're going to assume under our null hypothesis. So to work out the expected counts, you can think of proportions. We've got 40 students in Professor Alpha's class and 32 students in Professor Beta class. So if I wanted the expected value here for this one here, and you can see I've got the observed here expected, it's a neat way of just showing it all on the same table rather than doing two different tables, then one way to think about it is 40 out of the grand total 72 of both classes times the 12, or you could think of it as 12 out of 72 times the 40. The easiest way is just to do the row total times the column total and divide that by the grand total, which will give you the correct proportion of expected. So in other words, 12 times 40 out of 72 will give you 6.66. Equally, to get the expected in this cell, 12 times 32 out of 72 gives you 5.33. So you get the expected values. Now, one thing to notice here, which is really important, is we have one category. We've categorized the students by grades. The category is not really the professor. The professor is not a category, it's really a group. So when you have two groups, multiple groups across a category, that would be a homogeneity test. Later we'll do chi-squared test for independence, and that's when we've got a category on one axis and a category on another axis, so category versus category. Here we've got two groups of students, some in Professor Alphas, some in Professor Betas, and we want to know if they're marking the same or not, so it's homogeneity. More about that later. So now we've got the expected numbers, we see we've got a problem, because in the assumptions and conditions, we have to have basically our expected counts more than 5, and you can see we've broken that in D and F. And it does therefore make sense to combine D and F, because we cannot do a chi-squared test if the expected counts are less than 5. So let's now look at the assumptions and conditions and combine those D's and F's. So here we've combined D's and F's, and when I worked out the new expected count cells, they came out at 8.33 and 6.67, so that's good. All of our expected counts are now over 5. Now let's talk about the degrees of freedom. I've written the formula down here on the right. This is slightly different from goodness of fit. The degrees of freedom for a chi-squared homogeneity and chi-squared independence is the number of rows in your table minus 1 multiplied by the number of columns in table minus 1. So if we look here, we've now got, after combining cells, 4 rows and we've got 2 columns. So the degrees of freedom is 4 minus 1 multiplied by 2 minus 1. Giving us 3 degrees of freedom, which is quite a skewed chi-squared distribution, quite positively skewed. Now let me try to explain why it's that. I want you to imagine you know the totals in each column and row. So imagine you know 12, 23, 22, 15, 32 and 40. Really, all you need to know is 3 items to work out all of the others. Because if I know this item, I can work out that number. If I know this item, I can work out that number. If I know this item, I can work out that number. If I know these 3 items, I can work out that number, because you know the totals. And that's why the degrees of freedom is row minus 1 multiplied by column minus 1. Now let's talk about assumptions and conditions. Randomization, no, that's a major flaw. I've said it's okay as we're not making inferences, just looking at difference in this test, but actually I think it's a bit of a problem. I'd much rather this was an experimental design and we could actually randomly assign students to Professor Alpha and randomly assign students to Professor Beta. I'll talk at the end of this video about actually a better experimental design. The problem I have with this is that when a timetabler scheduler actually designs the schedule for a class, there's lots of confounding variables. In other words, what other classes the students usually take. So for example, in Professor Alpha classes might actually be all science students because they do other science subjects and it just doesn't fit, whereas Professor Beta's class might have all the musicians in, and that could be a confounding variable, I don't know. So it's better to be randomly assigned. Independence, let's assume that's okay. Expected counts, no, it was broken. We need to combine D and F, but now it's fine, and yes, it's counted data. So let's proceed with the mechanics. As always, in AP Statistics and Good Statistics Practice, make sure you identify your test. So we're going to perform a chi-squared test for homogeneity, and we're going to set the alpha level at 5%. So our null hypothesis H0, the grades from Professor Alpha and Beta are from the same distribution. And H1, the grades from Professor Alpha and Beta are from different distributions. This is a great indication, your alternate hypothesis, of whether you want to do a chi-squared test for homogeneity or independence. What do you want to say at the end? Here, it does make sense. If they are different, to say they're different rather than independent. So always think, as a statistician, what do I want to say at the end? And that guides you in terms of whether you're doing homogeneity or independence. Now you should always draw a picture, and I remember Mr. Dale, who was a fantastic teacher. He mentored me when I was in my younger years in Dubai College, and he always said never show some students that something that's wrong, because if you show them something's wrong, that's what we'll remember. So I've put a big red cross through because I want to show you don't do this. When you do your side-by-side bar chart to look at the actual numbers, don't have the number of students on the vertical axis, because of course there are different numbers of students in Professor Alpha's class to Beta's class. There were 40 in Alpha's and 32 I think in Beta's. So we need the proportions here. So this is a really, really bad diagram, and I just wanted to emphasize that, and now let's do a better. So here's a far better diagram showing, well, it's the other one would be dreadful. Now we've got the relative frequency of number of students, and we've got side by side of A grades, B grades, C grades, and the combined D and F. And you can see from the bar chart that Professor Beta has a higher proportion of students achieving A and B grades than Professor Alpha, and fewer C, D, and F grades. So make sure you do that diagram proportionally. The mechanics are identical to a goodness of fit. So goodness of fit, homogeneity, and independence, the mechanics are identical. Remember to always show the formula. So the sum of the observed minus the expected squared over the expected. You only need to show 3 calculations plus ... and then write down your chi-squared test statistic, which in this case is 9.32. You can choose to do it on your calculator, or you can choose to put the data into your TI and get the calculator to work out the chi-squared. So you can do it by hand using calculator, or do that. Sometimes I prefer it by hand, it's quicker, so you make the decision. Now don't forget to always draw the picture of the chi-squared distribution. It's positively skewed, the chi-squared 3 distribution. Show your test statistic, 9.32, and we want to know the probability of the p-value is getting 9.32 or greater. It's always one-tailed in chi-squared, because obviously we squared everything. So in your calculator you can enter chi-squared CDF. The test statistic is 9.32. Put 9999, that roughly represents going to infinity, and your degrees of freedom is 3, and out pops the number 0.0253. So 2.53%, and don't forget to say it's from your TI you've probably got 84s or inspires, and that's the mechanics there. Your final sentence as before, reject H0 in favour of H1 since P is 2.53%, which is less than 5%. There is evidence to suggest in this instance that the grades from Professor Alpha and Beta appear to come from different distributions. This is a statistically significant result. Now the test has proved to be statistically significant, but that doesn't show us where it's different. Our original side-by-side bar chart gave us some indication, but what we actually can do, which is more powerful now, once you've rejected H0, you can look at the standardized residuals to help you determine where those differences lie. So to work out the standardized residuals, you do the observed value minus the expected value divided by the square root of the expected value. And here, adopting that formula, here are the standardized residuals. So you can see I've written here a summary. The largest difference in standardized residuals is in the A grades. It appears that Professor Beta is more likely to give A grades than Professor Alpha. And we can see that because Professor Beta has a 1.59 standardized residual and a minus 1.42 for Professor Alpha. So that's the biggest swing. There is also a large difference in the residuals for D and F grades. It appears that Professor Alpha is more likely to give more D and F grades than Professor Beta. And again, a large-ish swing there as well in the D and F grades from 1.27 to minus 1.42. So, as I said at the start, I think we might have some confounding variables here. I think we definitely will, because the master scheduler would have had to take into account all of the other courses. I think what would have been really interesting is if we could have done an experimental design and randomly assigned Professor Alpha students and some to Professor Beta, and then randomly assigned within Professor Alpha student who Alpha is marking, so Alpha marking Alpha, and then Alpha marking some of Beta students, and then Beta marking Beta students, and Beta marking Alpha students. So then having 4 groups across maybe 4 or 5 categories, depending on our expected counts, and I think that would have been a far more robust experiment as opposed to an observation. Thank you very much for watching this video. I hope you enjoyed it. Please give me a thumbs up and subscribe to my channel if you did. And also I'm going to make a chi-squared test for independence as well, and we're going to look at the sinking ship, the Titanic. Have a great day, everyone.